In Chapter 8, we are covering independent samples t-test. In an independent samples t-test, we are comparing the means of two different samples. That is, these are independent samples, meaning that they are not connected to one another. This contrasts the dependent samples t-test in that a dependent samples t-test uses the same group twice, so those two scores are dependent upon one another. We're looking at changes from the means of the same group over two occurrences in a dependent samples t-test, but in independent samples t-test, we're looking at two samples from two different sets of people. So let's jump into the research question and hypotheses that will establish the purpose for hypothesis testing for an independent samples t-test. We're going to cover the two-tailed research question and the one-tailed research question, and then the two-tailed hypotheses and the one-tailed hypotheses. For a two-tailed research question for an independent samples t-test, we ask, is there a significant difference between two different samples? That is the general research question. You'll need to plug in your specific situation in order to bulk up the research question. For example, is there a significant difference in height between male and female students? That would be a way that you would bulk up that two-tailed research question. A one-tailed research question is there a significant increase/decrease, depending on which way you are hypothesizing, between two different samples? One way you could state this is there a significant increase in height between male and female students? Or is there a significant decrease in the time it takes to complete an exam between freshmen and seniors? So we can look at that in either direction. Notice that you have to pick one, you don't get both. The two-tailed hypotheses that go along with the two-tailed research question is as follows. The alternative hypothesis is the mean of group 1 is not equal to the mean of group 2, meaning that there is a significant difference. The two-tailed null hypothesis is mean of group 1 is equal to the mean of group 2. For the example that we plugged into the research questions, for the alternative hypothesis, we could say that the mean of females' height will not be the same as the mean of males' height. For the null hypothesis, the mean of group 1 is equal to the mean of group 2, meaning that there is no difference. In this case, the null hypothesis would be something like the mean height of women is the same as the mean height of men. So there would be some kind of non-difference between them. And that's a two-tailed hypothesis. Remember, we are not suggesting that one is different positively or negatively. We're just assuming that there is some difference somehow. For a one-tailed hypothesis, we are suggesting that there is a difference between the two groups and that we are suggesting a specific direction of change. So an alternative hypothesis would be the mean of group 1 is less than the mean of group 2, or the mean of group 1 is greater than the mean of group 2. And that depends on the way you are hypothesizing the change. And the null hypothesis is, as you would expect, the mean of group 1 is greater than or equal to the mean of group 2, or the mean of group 1 is less than or equal to the mean of group 2. In either of those cases, you are hypothesizing that there is a similar score between the groups, or that it is in a direction that you did not hypothesize. So as you look, the null and research hypotheses are clustered this way, so these two go together, and on the other side, those two go together. So make sure that when you decide to do a one-tailed hypothesis, you are using the correct signs. The big idea with the independent sample t-test is that we need to find the mean of each sample, usually pretty easy. We need to find the differences between the scores, so how far apart are the means? And then we need to calculate the estimated population standard deviation, S, of the differences between the means of the different scores. That's a mouthful, we're going to unpack it, but that's how it is. And then we plug that information into a very simple T formula. What we are trying to find out is how far away are the differences between the two means compared to a situation where we would expect no difference. Remember, the null hypothesis in most cases is that we expect no difference between the two groups. And we want to know how far away our differences are from a situation where there is no difference. So we do that by using the formula. The t-score is equal to the score of group 1 minus the score of group 2. So we're going to find the differences divided by the standard deviation of the differences between the groups. So this follows the same formula as we've been looking at in other tests, which we'll take a look at in a second. Let's get through the big idea first. So we are testing if the differences between the means are significantly different from a situation where the differences are 0. For example, if we had two scores, it doesn't matter what the scores actually are here. If we had two means from two different groups and their curves overlap this way, are the differences between those two groups significant? And that's what we're looking to test. Is there a significant difference in the means of the groups when we consider the fact that the scores will overlap one another somehow? So again, we're looking at some formulas. The Z formula, when we talked about Z-test, is that the score of an individual minus the mean of some scores divided by the standard deviation. We want to know if the scores are different, and if they are, how far away are those differences from each other. The t-test for a single sample, or the single sample t-test, is that the mean of a group minus the mean of the distribution of means, which is based on the population, divided by the estimated population standard deviation distribution of means. We want to know if that is significantly different from a situation where there is no difference. Same thing. In a independent samples t-test, we want to know if the mean of group 1 minus the mean of group 2, let's fix that real quick, minus the mean of group 2 divided by the standard deviation of the difference between the means is significant. We're trying to find that out in the independent samples t-test. Is there a significant difference between the two groups? That's all we're trying to do, and it follows the same type of formula. Something minus something else divided by the standard deviation. Something minus something else divided by the standard deviation. Something minus something else divided by the standard deviation. T-test, Z-test, and F-test all kind of rely on that same kind of formula. F-tests are a little bit different, but we'll talk about those when we get to ANOVA. The formula that we looked at, the mean of group 1 minus mean of group 2 divided by the standard deviation of the difference between the groups, is relatively simple when we think about it from a conceptual standpoint. The top part is very easy. We're looking at the difference between two scores, the mean of group 1 and the mean of group 2. How far apart are those means? Well, that's easy to calculate. The hard part is this denominator. We want to also figure out, in addition to how far the scores are apart from one another, how much those scores overlap one another, which is what we find out by looking at the difference between the standard deviations. The hard part is the denominator. We want to know what the standard deviation of the differences between the means are. We want to know that. In order to find that, get ready, we use this kind of formula. It's okay. We'll get through it together. It's a fairly simple idea, but we have to look at it in each step to find out what the estimated population standard deviation of the differences between the means are. That's all we're trying to do, is to eventually get to this point where we have the bottom of the formula. So here's how we start. We need to take each sample. Remember, at the very basic, we are talking about two samples, and we want to know what the variance of those samples are, in addition to the mean, which is easy to find out. But the variance of each group is found out using the variance formula that we've become familiar with from the chapter when we talked about single sample t-test and dependent sample t-test. We take the sum of squares divided by the degrees of freedom for sample 1. So the estimated population variance of sample 1 is the sum of squares divided by degrees of freedom. We do the same thing for sample 2. the estimated population variance of sample 2 is equal to the sum of squares for that sample divided by its own degrees of freedom. And if degrees of freedom are throwing you, remember degrees of freedom equals n minus 1. So it's a number in each sample minus 1. Once we have the variance of each of those samples, we want to find out how much each sample's variance contributes to the overall variance between the two groups. Now think of it this way. We have two groups of people. We want to find out how much variance is in the groups, but we also want to find out how much each group contributes to the variance. Let's say that we had 10 people in one group and 100 people in another group. The variances between those two groups would likely be different, and the amount of variance that each group contributes is different because one group's going to have a lot more variance than the other. We know that a group of 10 people is likely to have a lot more variance than a group of 100 people. So we want to know not only what each group's variance is, but also how much each group contributes. So what we do is we calculate what's called the weighted variance between the samples. So we're going to find out how much each sample's variance weighs, how much it contributes. So what we do is we take the degrees of freedom in sample 1 divided by the degrees of freedom total. That gives us the ratio or the weight of that particular variance. So we find out how much of that sample contributes to the weight and multiply it by that sample's variance. So we take the sample's variance and multiply it by a weight. We do that for both samples. We have the weight of the second sample multiplied by that sample's variance, and that tells us how much this sample weighs, sample 2, and it also tells us how much sample 1 weighs. And we add those together, and that gives us an overall pooled variance. It tells us how much variance is in each sample when we add them together. So this is one number, the pooled variance. Once we have the pooled variance, this tells us how much variance is between the two groups. The next step then is to convert each sample into a distribution of means. Because remember, we're still comparing the mean of a group of scores to an estimated population that is the mean of, or that is of a bunch of individual scores. So again, we're comparing the mean of two groups to a situation where there are individual scores. We have the estimated population variance of the distribution of means for sample 1 is equal to a very simple idea, the total amount of variance between the two groups divided by the number of people in that first sample. It's the same kind of process that we talked about in step 2 when we talked about converting a distribution of individual scores to a distribution of means. We took the variance of the sample. In this case, it's the estimated population variance, not of the sample. Estimated population variance and divide it by the number in the sample. We do the same thing for the second sample. We take the second sample's estimated population variance and divide it by the number in each sample, in the second sample, and that gives us our estimated population variance of the distribution of means of the second sample. So again, it's just that pooled variance, the total amount of variance, divided by the number of people in that sample, and that gives us our distribution of means for each sample. Once we have the distribution of means for each sample, then what we can do is find out the total amount of variance in the distribution of means. Remember, we're trying to build this comparison distribution that we are going to compare our sample's variance to. So what we're going to do is calculate the total amount of variance in our distribution of means, and that becomes what we call the difference in the variances for the distribution of means. That is the total amount of variance that occurs between the two groups' distribution of means. Once we add those together and get the sum of the variances of the differences to two samples, then we can calculate the standard deviation of the differences between the two samples. And whenever we have the variance, we can take the square root of it, and that gives us our standard deviation of the differences between the two samples. Then we can go into our formula. We want to find out the difference between the two groups divided by the total amount of standard deviation, or the standard deviation of the differences between the groups. And we plug in what we got from the last step into the new denominator of that formula, and then we can go forward. Now, I know we've been talking about this just without any real numbers attached to it, so we're going to step through a couple processes that will get us to calculating the estimated population standard deviation of the differences between the means. So let's go ahead and do that now. This is just a simple example based on some random data. It doesn't really matter where the data comes from. I want you to walk through this structurally. But if you must have some kind of context for it, let's say that we have two groups of people, and let's say that these are two different classrooms, and let's say that these are of children who misbehave. So you have two smaller classrooms where people who misbehave go. That way they can get better attention, et cetera, et cetera, et cetera. And let's say group one is one teacher and group two is another teacher there. And the numbers represented here are the number of outbursts that each child has per day. So this is a classroom of 5 people, and this is a classroom of 2 people, and these are the number of outbursts that each child had per day. So child 1 had 2, child 2 had 3, child 3 had 6, child 4 had 4, child 5 had 7, et cetera, et cetera. So here's what we do in order to find that S difference value. First thing we need to do is we need to calculate the estimated population variance for each group. Remember, that's that S2, estimated population variance of group 1, estimated population variance of group 2. This is the math that we work through in order to get to that point. I trust you can walk through that, at least understand where we get those numbers from. I don't feel like we have to take the time to work it out by hand. You can see what it looks like. So from each group, we have some figures. Group 1, the mean of group 1 is 4.4, so on average, the kids have 4.4 outbursts per day. And for group 1, the number is 5, degrees of freedom is 4, and the estimated population variance is 4.3. For group 2, we have a mean of 4.5, number equals 6, degrees of freedom equals 5, and the estimated population variance of group, and that should say 2, and the estimated population variance of group 2 is 2.3. So we have some information that we can plug in. Now let's go forward using our method that we looked at from a couple slides ago now. So we need to find out what the pooled variance is, so the total variance between those two groups. And we do that by plugging in some information. So we know from last slide that we have degrees of freedom for each group, and we also can add together degrees of freedom and tell us what the total is. So for group number 1, which had 5 people, the degrees of freedom are 4, the total degrees of freedom 9. That's the total degrees of freedom for the two groups. And we know that group number 1 had an estimated population variance that equaled 4.3. And for group 2, we had 6 people, so that means that the degrees of freedom is 5 divided by 9, because that's the total degrees of freedom, not equals, times the estimated population variance for group 2, which was 2.3. Doing a little bit of math, 4 over 9 is equal to 0.44 times 4.3 plus 0.55 divided by, multiplied by 2.3. And then we keep doing math, and that equals 1.89 plus 1.26, which equals 3.15. So the pooled variance for these two groups is 3.15. So the total amount of variance between these two groups is 3.15. That's 3.15 outbursts if you're playing along with the example. Now, once we get the pooled variance, then we can move on and calculate the standard deviation, or excuse me, the variance of the distribution of means for each group. So for each group, you're going to have a different estimated population variance of the distribution of means, and we use it by calculating the pooled variance that we found from the last step, and for each group dividing it by the number. So in this case, the estimated population variance of the distribution of means for group 1 is equal to the pooled variance of 3.15 divided by the number in the sample, and the number in the first sample was 5. And then we do the same thing for group 2. The estimated population variance of the distribution of means for group number 2 is equal to 3.15, which is the pooled variance, divided by 6, which is the number in the second sample. And then kind of bouncing back and forth a little bit, the estimated population variance for the distribution of means for group number 1 is equal to 3.15 divided by 5, which is equal to 0.63. And for group number 2, the estimated population variance of the distribution of means for group number 2 is equal to 0.52. So this is the estimate of the population variance of distribution of means for each group. Now our next step is to find the differences between those, the total amount of variance difference between the two distribution, or excuse me, between the two distribution of means for each group, because each group would have one on its own. So the estimated population variance of the differences between the means is equal to the estimated population variance of the distribution of means for group 1 plus the estimated population variance of the distribution of means of group 2. We found those both in last step, so the combined amount of variance in the distribution of means for each of those is 0.63 plus 0.52, which is equal to 1.15. So the total amount of variance between the differences of those groups is 1.15. Then the next step to get the standard deviation of the differences between the means is to take the variance and divide it, or take the square root of the variance, which is equal to the square root of 1.15, which is equal to 1.07. So what we've done here is created a distribution of means that allows us to look at the difference between the groups to find out if the difference between the groups is significant compared to a situation where there is no difference, meaning 0. Graphically, what this looks like is we now have a comparison distribution. If we think that the null group or the comparison distribution has a mean t-score of 0, meaning that on average there would be no difference, then the standard deviation of the distribution of means is going to be -1, -2. Estimated population standard deviation of the differences between the groups is equal to 1.07. Differences, we expect the differences to be 0. The t difference would be 0, and so would the raw score difference. We expect the raw score difference to be 0, but to have a standard deviation of 1.07. So that means that we have a raw score of 1.07 and 1.14, and then negatively we have -1.07 and -1.14. This is our comparison distribution. If the differences between our two means fall within a critical range, which we're going to find in the next slide, then we have a significant difference. If not, then we have a non-significant difference. But the idea is that we now have a distribution of means that's based on a mean difference of 0, because remember, if the null hypothesis is true, then there is no difference between the means with some kind of standard deviation, and the t standard deviation is always 1. And the x or raw score standard deviation is based on what we found when we calculated the estimated population standard deviation of the differences between the means. It's 1.07. In order to continue to build the formula, we need to kind of finish the example, and I know that we're kind of jumping around the hypothesis testing procedure to do this, But I think that by now we can kind of follow along and recognize that once we have our t-value, then we have something to compare our results to. So in this particular case, we have an example where we have a situation where we want to know if there is a significant difference between the scores of two groups. And we're going to use a conventional cutoff of 0.05, alpha level equals 0.05. Two tails, because we're just concerned about some kind of change. We want to know if there is a difference between the two groups in terms of their behavior, for example. And the degrees of freedom is equal to 9. That's the total degrees of freedom. Group 1 has 5 people, group 2 has 6 people. So that means that 5 minus 1 is 4, 6 minus 1 is 5, and 5 plus 4 equals 9. That's the total degrees of freedom. In my t-table, I found that the cutoff score for the parameters that we have set for our cutoff is equal to positive or minus 2.62, which I've placed on our comparison distribution. And remember, these are the differences. So if the difference between our two groups is greater than positive 2.62 or less than negative 2.62, then we have a significant finding. So let's go ahead and calculate our t-statistic to find out if we have a significant difference between the groups. T is equal to the mean of group 1, which was 4.4, minus the mean of group 2, which was 4.5, divided by the standard deviation of the difference between the groups, which was 1.07. That is equal to 0.1. The difference between the means is 0.1, but it's negative because 4.4 minus 4.5 is negative 0.1, divided by 1.07 is equal to negative 0.09. So the difference between our two groups has a change of negative 0.09 in terms of the t-value. The t-value is negative 0.09. So it is 0.09 standard deviations below the mean. It's so close to the mean. It's hard to draw how close it is to the mean. It's not even 1/10 of a standard deviation away from the mean, meaning that it's really close to what the mean is if you estimate it to be 0 based on the fact that we have a null hypothesis that says that there is no difference. This is negative 0.09. Now, based on a visual inspection, you can kind of see that we're going to fail to reject this. We needed this score to be much more extreme than it was. So the difference between the two groups is not significant based on our visual inspection. But let's go ahead and do what we do with our null hypotheses. So the null hypothesis for this two-tailed test is that the mean of group 1 will be the same as the mean as group 2. And really what we know is that we want to find out if our t-score falls between our cutoff scores. So the cutoff t-score in this particular case was negative 2.62 and positive 2.62. In order for this statement to be true, we know that our actual observed t-score needs to fall between that. So if I put our t-score of negative 0.09 and then I put in our symbols to find out if there is a difference, we can test to see if there is a significant difference based on our null hypothesis. And by the way, this is step number 5 in our hypothesis testing procedure. This is step number 4. This is step number 3. I know we're kind of clustering it all together, but here it is. So we need to check and see if these two statements are true. So let's find out. Is negative 2.62 less than or equal to negative 0.09? Yes. So far it looks good for the null hypothesis. Let's check the other side. Is negative 0.09 less than or equal to positive 2.62? Well, that answer is also yes. That means that we have two confirmed statements here indicating that we accept the null hypothesis or that we failed to reject it. So in this particular case, we have a failed to reject situation in that there is not a significant difference between the differences between the two groups. If there were a significant difference, then the differences between the two groups would be in our rejection zones. We do not find that, therefore we fail to reject the null hypothesis. So that's a rundown of the changes that go on between a dependent samples t-test and an independent samples t-test. We're going to run through an example right now from start to finish using the hypothesis testing procedure that allows us to step through each aspect individually rather than looking at it in its whole. Let's get some data, and for this example I'm going to make it up. The question is, what is your stance on caffeine? Just kind of an interesting survey point. And we want to know if there is a significant difference between some two groups and their stance on caffeine, where 1 is, I couldn't care less, don't need it, and 7 is, I need it intravenously. I know who you are. We want to find out how to manipulate the independent variable, which kind of makes it sound awful, but manipulation is good in this case. So sometimes we just go with simple things like male or female or something else. So let's go with something else in this case. Let's say that I want to know if there is a difference between caffeine consumption for morning people, so those people who are morning people, and those people who are not morning people. And I want to know if there is a significant difference in the means of people who are morning people and not morning people. For the sake of it, let's just call this group number 1 and group number 2. We're just assigning a number to the group, that way we can keep it straight. So I'm going to make up the example and see if we can't find something here. And we're going to kind of assume that we don't know if there's going to be a significant difference in a positive or negative direction. We're just trying to find if there is a difference. Because theoretically, maybe morning people like coffee so much, that's why they're morning people. Or maybe morning people don't need coffee, and so they really don't care about caffeine. So let's go ahead and find out. So again, it's made up, so we're not going to really find out anything, but you know what I mean. So let's say that I polled 12 people, and the morning people rated their caffeine needs as follows: 5, 6, 4, 4, 7. So that's 5 people in group 1. Group number 2, let's say that they rated their caffeine consumptions like this: 6, 6, 4, 1, 7, 2, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. That means we have 12 people. We have n equals 7 in one group and n equals 5 in another group. So we have to walk through this hypothesis testing procedure, and we're going to do it step by step. Step 1 is to identify the populations and the research question, and we're going to do that by coming up with a research question. The research question that we're going to use is there a significant difference between morning people and not morning people in terms of their caffeine consumption? So I'm going to abbreviate it. Is there a difference between AM and not AM people? Question. See, research question. And it's going to be two-tailed, so we're going to use a two-tailed alternative hypothesis, and I'm going to abbreviate that too, and that the mean of group 1 will not be the same as the mean of group 2, and the null hypothesis is going to be that the two groups are equal. Mean of group 1 equals mean of group 2. You will need to make sure that you express that very clearly when you do your data analysis. Don't just say this, you need to say the mean of group 1 of morning people will not be the same as the mean of group 2 who are not morning people, or some other way elaborate on that. So we are going to be testing our null hypothesis to determine significant differences. And in step 2, we are going to determine the characteristics of the comparison distribution. And because we have some raw data, we really need to be careful to do all the steps we need to do beforehand. So the raw data is that we need to calculate some kind of mean and measure of dispersion for each sample. We have 2 samples. And remember, we're not going to be asked to do this by hand, but we do need to be familiar with the steps to walk through it. So we need to, for each sample, find the mean and the estimated population variance. And we do that by listing the scores for each group. So the scores for group 1 are 5, 6, 4, 4, 7. And I'm going to write out the rest just because it makes it a little bit easier. So x minus m equals negative 0.2, 0.8, negative 1.2, negative 1.2, and 1.8. And by the way, mean is equal to 5.2. N is equal to 5. And degrees of freedom is equal to 4. Keep going now. X minus m squared is equal to 0.04, 0.64, 1.44, 1.44, and 3.24. And then the sum of squares, remember sum of squares is the sum of all the square deviation scores, is equal to 6.8. And then the estimated population variance is equal to 1.7. So this is for group number 1. Now, group number 2 has its own information as well. So for group number 2, we have some scores. Group number 2's scores are 6, 6, 4, 1, 7, 2, 7. And group number 2 has a mean, has a number, and has some degrees of freedom. And the mean of these 6 scores is approximately 4.7. And I'm going to round to 4.7 because it's a long decimal. 4.7, number is 7, degrees of freedom equals 6. X minus m, 1.3, 1.3, negative 0.7, negative 3.7, 2.3, negative 2.7, and 2.3, and those figures squared, I lost a negative sign. Those figures squared are equal to 1.69, 1.69, 0.49, 13.69, 5.29, boy, this is boring, isn't it? 7.29, and 5.29. The sum of squares is equal to 35.43. And then the estimated population variance is equal to approximately 5.9. We're going to use 5.9. So each of these samples has its own characteristics, and I'm going to go ahead and plug in the estimated population variance for each one, 1.7, and estimated population variance for group 2, maybe I'll be more careful, group 1, and of group 2 is equal to 5.9. So this is step 1 of step 2 of finding the characteristics of the comparison distributions, but we also need to find out some information about the comparison distribution in addition to this. So I brought forward some information from the last slides, including bringing forward the formula that we're going to work toward. So remember, we're still trying to find the comparison distribution that we're going to use to compare the differences in our scores to. In order to do that, we need to find out what the spread of the distribution of means is, which is the S diff that we're going to find. So the first step that we do is we find the pooled variance between the two groups. And you can check out that formula by rewinding the video or taking a look at your notes. But essentially, we're going to take the degrees of freedom in the first group and divide it by the total degrees of freedom. So the degrees of freedom in the first group is 4. The total degrees of freedom is 10. 4 divided by 10 times the estimated population variance for group 1. I just plug in the number, not the thing. The estimated population variance from group 1, which is 1.7. Okay, plus the degrees of freedom in group 2, which is 6, divided by the total degrees of freedom, which is 10, times group 2's estimated population variance, which is 5.9. And when we multiply that out, we get 0.4 times 1.7 plus 0.6 times 5.9, which equals 0.68 plus 3.54. And 0.68 plus 3.54 is 4.22. So the total amount of variance is 4.22. Now, after that, we calculate each sample's distribution of means. And we do that by taking the variance of the distribution of means from the first group, which is equal to the pooled variance divided by the number in the sample. So the estimated population variance of the distribution of means of group 1 is equal to the pooled variance for the groups that we found in the step above, 4.22, divided by the number in the sample, and group 1 has an n equal to 5. The estimated population variance of the distribution of means of group 2 is equal to the same pooled variance, 4.22, divided by the number in that sample. And that sample had 7 people in it. Do a little bit of math and we can get the answer. In the first group, the estimated population variance of the distribution of means is equal to approximately 0.84, and in the second group is equal to approximately 0.60. Now, the next step is to find the estimated population variance of the differences between those groups. So what we do there is we just add together the variances, and that gives us the total amount of variance in the distribution of means. So the variance of the difference of the distribution of means is equal to the estimated population variance of the first plus the estimated population variance of the second, which is equal to 0.84 plus 0.60, which is equal to 1.44. So the variance of the differences between the groups is 1.44. And in order to get the standard deviation of the difference between the groups, all we do is we take the square root of what we found in that step. So the square root of 1.44 is equal to 1.2. So what we have just found is the estimated population standard deviation of the differences between the means. That allows us to do two things. It allows us to plug into our formula, and it also allows us to create a distribution of means that we can compare our sample to. So let's go ahead and just draft that out now and take. So I can plug in my distribution of means curve, and I can plug in some information. we know that we're expecting there to be no difference. So our t-score is equal to 0, and so is our x-score. So 0, 1, 2, -1, -2. Our raw score in this case, if there is no difference, we expect it to be 0, the difference between the two. So the mean difference we expect to be 0 if the null hypothesis is true. The spread of this distribution of means is equal to this S difference character of 1.2. So 1.2, 2.4, and then -1.2 and -2.4. So if the difference between our means is somewhere on this curve that constitutes a cutoff, then we will reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. So what we're going to do in this step also is kind of move into step 3. So kind of a step 3 situation is to determine the cutoff score where we'll reject the null hypothesis. We're going to use a conventional cutoff level equal to 0.05. We're going to use a two-tailed hypothesis. And we need to calculate the total degrees of freedom. The degrees of freedom in this case is equal to 4 plus 6, so our degrees of freedom equals 10. When I consult a t-table, a two-tailed test at the 0.05 significance with 10 degrees of freedom, we're looking at a cutoff value equal to 2.228. So our cutoff t is equal to 2.228, and that's positive or negative. So we're looking at a cutoff in this kind of area, 2.228, positive or negative, sorry about that. Or negative 2.228. So we're looking at a cutoff there. And we will reject the null hypothesis if it falls in either of those two. Otherwise, we fail to reject the null hypothesis. So let's go ahead and clean the slate and take a look at step number 4, where we actually calculate what our sample's t-statistic is, which is something that we started by looking at this formula at the top. So let's go ahead and take that to step number 4 and calculate our sample's actual t-statistic in terms of how different it is from a situation where there would be no difference. So in step number 4, we're going to calculate the test statistic to find out if it is significant compared to our comparison distribution. So we're going to use the formula t is equal to the mean of group 1 minus the mean of group 2 divided by the estimated population standard deviation of the differences between the means, S diff. That is equal to our first mean, and the mean of group 1 is 5.2 minus the mean of group 2, which was equal to 4.7. We divide that by the estimated population standard deviation of the differences between the means, which is effectively the standard deviation of the distribution of means, which is equal to 1.2. We carry this forward. 5.2 minus 4.7 is equal to 0.5. So we know that there was that group number 1 had a 0.5 or half of an outburst per day compared to group number 2. So there was an increase in group number 1. Divided by 1.2 is equal to approximately 4.2. It's 4.16 repeating. .42. Now, if we bring forward the comparison distribution, we can kind of look at this graphically to find out if there is a significant difference. So graphically, we can plot our sample's t-score, which we found to be 0.42, onto this, and it looks like it's going to be just under half of a standard deviation above the mean. So our t is equal to 0.42. So it doesn't look very good for our alternative hypothesis because visually we don't look like we're going to be inside of that rejection zone. So let's go ahead and go forward with step number 5. We can plug in step 5 on the same page, no problem. Step number 5 is to determine if that difference is significant. And we do that by testing our null hypothesis. Our null hypothesis was that mean of group 1 would be equal to the mean of group 2. We know that when we have a two-tailed hypothesis, we have to test to see if our sample score is above or below negative 2.8 or above or below positive 2.28. So let's go ahead and plug in our critical values, negative 2.28 and positive 2.28, to determine if there is a significant difference or not. And we do that by plugging in our t-score, our sample's t-score of 0.42, and we want to test these inequalities to determine if there's a significant difference. And remember, if we can reject either one of these sides of the equation, then we can reject the entire null hypothesis, which would mean that we have a significant finding. So let's find out. Is negative 2.28 less than or equal to 0.42? Well, the answer to that is yes. So this side of the equation supports the null hypothesis. The second half, is 0.42 less than or equal to positive 2.28? The answer to that question is yes. That means that we have two checks. We support the null hypothesis. So this is what we call a fail to reject. We failed to reject the idea that the two groups are similar. What we can conclude is that the two groups had means that were not significantly different from one another. If they were significantly different from one another, then they would have a t-value greater than 2.28 or less than negative 2.228. So we can conclude that we failed to reject the null hypothesis that the two groups have relatively similar means. So, that's the big dang deal for independent samples t-test. We really went through a lot in that lecture, I know. But what I want you to be able to do is apply this information to recognizing what the results look like when we go through SPSS and interpreting and making decisions about the null hypothesis testing procedure. Do take a look at anything that's available to you in terms of additional resources. But remember, the big deal about independent samples t-test is being able to determine if there's a significant difference between two different groups, and we do that by testing to see if the differences between the two groups is significantly different than 0. If it is significantly different than 0, then you know the two groups are different. If not, then the groups are not different than one another. So whenever you get stuck, remember to always back out and try to get to the broad picture so you can get a better understanding of this stuff. If you have any questions, always reach out, and we will catch you next time.